Hi, hello, welcome. This is Discrete Mathematics, and today we are talking about section 3.3, relations. We're going to define what relations are, look at the differences between relations and functions, which we talked about in our last video. We'll discuss different examples of relations and learn about some properties and then some special types. So first up, what is a relation? A relation from one set to another is simply a set of ordered pairs. It's a way of relating elements of one set to elements of another set. It can be thought of as a table which shows how elements of the first set relate to elements of the second set. It can also be thought of as an arrow diagram. So a binary relation, R from set X to set Y, is a subset of the Cartesian product X cross Y. If xy is in R, then we write xry. If x is equal to y, we call R a binary relation on X. A function is a special type of binary relation. We talked about functions before. A function f is a relation with these two properties. The domain of f is equal to x. So every element in the first set in X is being used. And set 2, for all x in X, there exists exactly one y such that xy is in f. So here we are seeing no repeats. That's what it means to be a function. So we say that this first one is f is defined. If it's defined, then every element of X is being used. And we say that it is well defined if it meets this second property. There's exactly one y such that xy is in f. So that's no repeats in our x's. So R is a more general form than F. F is a special type of relation. Relations don't have these two restrictions. We can still talk about whether or not relations have one or more of those. Here we have our first example, example 1. Let R be a relation from X to Y where X is equal to the set Tom, Jane, and Susie, and Y is equal to the set Calc, Soc, and Discrete Math. And R has the rule person X takes course Y. I want to draw an arrow diagram. I want to know, is R a function? If not, is it at least defined? Is it well defined? And then here is R. R is the set where Tom takes Calc, Tom takes Soc, Jane takes Calc, Jane takes Soc, and Jane takes Discrete Math, and Susie takes Calc. So let's first draw the arrow diagram. This is X. This is Y. All the elements of X are Tom, Jane, and Susie. Elements of Y are Calc, Soc, and Discrete Math. So I'm ready to draw my arrows. Tom takes calculus. There's my arrow. Tom takes Soc. Jane takes Calc. Jane takes Soc. Jane also takes Discrete Math. And Susie takes Calc. So is R, next question, is R a function? If not, is it defined or is it well defined? So let's see. It looks like the domain of F is equal to X. So we're using all of these elements of X, Tom, Jane, and Susie. So that means that F is defined. Well, maybe I'll not call it, I'll call it R. This is R. R is defined. And that's all X's are used. Is there such a case where there's an X value that takes more than one Y value? And then the answer to that is yes. Tom goes to Calc and Soc. Jane goes to all three. So R is not well defined. And that's because of Tom and Jane take more than one Y value. So because it's not well defined, R is not a function. R is not a function. Okay, let's take a look at the next one. Example 2. Let X be 2, 3, 4, and Y be 3, 4, 5, 6, 7. We define a relation R from X to Y by XY is in R if X divides Y. Another way to say that is XRY if X divides Y. I want to draw an arrow diagram, talk about is it a function, is it defined, is it well defined? Let's first write out what our relation is. What are the elements in our relation? So we're looking for two values, an X value and a Y value, where X divides Y. So let's see, 2, does 2 divide any of these? 2 divides 4. 4 divided by 2 is 2. So we can do that. 2 also divides at 6. We can put that there. And I think that's it. Next up, 3. 3 divides 3. 3 divided by 3 is 1. And 3 also divides 6. And then 4 only divides itself. And then that's it. All right, so now that I have my ordered pairs all written out, it'll be a little bit easier to draw my arrow diagram. Here's x, 2, 3, 4. And here's y, 3, 4, 5, 6, and 7. And for my arrows, let's see, 2 goes to 4, 2 goes to 6, 3 goes to 3, and 3 goes to 6, and 4 goes to 4. Looks like we did not use 5 or 7. Our relation R is defined. That's because we used 2, 3, and 4. We used all of X. But is it well defined? It is not well defined. It is not well defined, and that's because 2 goes to 2 different things, and so does 3. 3 also goes to 2 different things. So it is not well defined, which means it is not a function. R is not a function. So now we have a kind of a second scenario here. What if I changed x to be 2, 3, 4, and 8? So I'm adding an 8 down here. Let's go back and revisit our relation. If I put an 8 in here, I need to figure out, does 8 map to anything in y? And the answer to that, I think, is no. 4 is divisible by 8, but we're looking for, does 8 divide anything in here? And the answer is no. So I would add this to my arrow diagram, but not have an arrow pointed any direction. So if I changed x to be that, now we're seeing that R is no longer defined. R is not defined because 8 does not map to anything in y. 8 doesn't map to y. So it's not part of the domain. I mean, the domain is not the same thing as x because 8 is not used, but it is a member of x. So R is not defined, so that it's also not well defined, and it's still not a function. Okay, let's take a look at example 3. We can define relation R on x, which is 1, 2, 3, 4, by xry if x is less than or equal to y. So we're going to do all the things, arrow diagram. Let's take a look at that. Our relation is going to be a set of ordered pairs. Since x isn't too big, we can write out the set of ordered pairs. We'll see in future examples where our sets are going to be a little bit too big to do that, but I think we can still do that here. We're looking for x less than or equal to y. So 1 is less than or equal to 1. And this is, I guess this is an important thing. We're looking at x times x. So x is the first values, and then also we're looking for x to be the second values. X is the x values and the y values. So y is also equal to 1, 2, 3, 4. It's equal to x. That's what we're saying, x cross x. Okay, so 1 is less than or equal to 1. 1 is less than or equal to 2. 1 is less than or equal to 3. And 1 is less than or equal to 4. And now we'll start with 2. 2 is not less than or equal to 1, but it is less than or equal to 2. And 3. And 4. 3 is less than or equal to 3 and 4, and 4 is less than or equal to 4. So those are the elements in our relation. We can draw an arrow diagram. It's going to have a lot of arrows on it. X, and this is another X. 1, 2, 3, 4. 1, 2, 3, 4. For our arrows, 1 goes to 1, and 2, and 3, and 4. So I'm seeing already that this function is not going to be well defined because this x goes to too many things. 2 goes to 2, and 3, and 4. 3 goes to 3, and 4, and 4 goes to 4. There is our arrow diagram. As we see our set get bigger, we see these arrow diagrams looking more and more chaotic and less helpful. And we're going to look at here in a little bit a different way to visually represent this that looks a little cleaner. Okay. Here's that way that I just talked about. Right away, we're going for it. One can represent a relation R on X with ordered pairs or by using digraphs. A digraph is a directed graph. Represent the digraph using vertices and directed edges with possible loops. So we're going to draw a digraph for relation R where R is AA, BC, CB, and DD. So here's A, B, C, D. Let's see, A goes to A, so here is a loop, A going to itself. B goes to C. C is actually going back to B. And then D is going to itself, so here's another loop. So we see two loops, and then we see a little circuit here with B and C. Let's go back and draw the digraph for this one up here. Maybe I'll do it in a different color. This is 1, 2, 3, 4. All right, 1 goes to itself, so there's a loop. 1 goes to 2, 1 goes to 3, and 1 goes to 4. And then 2 goes to itself. There's my loop. 2 goes to 3, 2 goes to 4. 3 goes to itself, and 3 goes to 4, and 4 goes to itself. So there's my digraph. That's maybe a little bit easier to look at than this arrow diagram. All right. Next up, definition. A relation R on X is reflexive if X, X is in R for all X's. So we'll see what this looks like. This is the first of the properties that we're looking at for relations. I mentioned at the beginning we're looking at properties of relations. We're going to look at a number of properties. This is the first one. So we're saying that XX is in R for all X's. Let's see what that looks like, what that means. Let R be a relation on X, which is A, B, C, D, where R is AA, BC, CB, and DD. So that's this graph that we saw up here. Is R reflexive? So that would mean that XX is in R for all the X's. So we see AA in R, and we see DD in R, but it's not reflexive. And that's because BB and CC are not in R. What would we need to add to R to make it reflexive? Well, we would need to add BB and CC. So what would this look like in our graph? If we added BB and CC, then we would have every vertex would have a loop. That's what a reflexive digraph would look like. Every vertex has a loop. That is reflexive. If we come back up to this graph in example 3, this one is reflexive. And that's because every every vertex has its loop, and we can see the coordinates or the ordered pairs here that make that happen. That's 1, 1, 2, 2, 3, 3, and 4, 4. So this one is reflexive. All right, let's take a look at our next property. A relation R on X is symmetric if for all X and Y in X, if XY is in R, then YX is in R. So we're seeing this flipping of the coordinates. That's symmetric. Here we have our familiar graph. Oh, actually, no, this is not a familiar graph. This is close to our familiar graph. Let R be a relation on X, which is ABCD, where R is AA, BC, CB, DD, but also AC. This is a new one that we added that wasn't in the last one. Let's draw the digraph and see what it looks like. A, B, C, D. So AA, there's a loop, BC, and CB, DD, AC, AC, and DD. So this one's not reflexive. We're missing CC and BB. But is it symmetric? Let's see. So we've got this one. So we have BC and CB. That is a symmetric relationship, and we can see that here in the graph with this circuit between B and C. But we don't have a matching thing for AC. So it is not symmetric because AC is in R, but CA, the opposite of that, is not in R. So what we would need to see in logic notation, if you remember from chapter 1, for all x and all y, if x, y is in R, that implies that yx is in R. So we are not seeing that here. We were able to find a counterexample. AC is in R, but CA is not in R. If we wanted to make this one symmetric, we would add CA, we would add this, and then it would become symmetric. Here's our property. If R is symmetric, then edges between two vertices must be in pairs with opposite direction. So if you go one way from a pair, then you have to go the other way as well. You don't have to include every single pair. Like if I would add this purple line, this graph would be symmetric. I don't need to add pairs everywhere. Anywhere I have one, I have to have a second one as well. All right, we're ready to move on to a new definition. A relation R on X is antisymmetric if for all x and y in X, if xy is in R and yx is in R, then X is equal to y. So what this is saying is there's no symmetry unless x and y are the same. So this stipulation here allows for loops. Because if x is equal to y, then x in R means that x is in R. So we're allowed to have loops, but we're not allowed to have any of the paired vertices in opposite directions like we had in the last one. All right, example 6. Let R be a relation on X, which is ABCD, where R is AA, BC, CB, AC, and DD, same as the last one. Is R antisymmetric? What element could we remove to make it antisymmetric? Is it possible for a relation to be neither symmetric nor antisymmetric? So here we are seeing we've got a couple loops, and we said loops are allowed. But the trouble I see is this pair is symmetric. So it's not antisymmetric. Because BC and CB are both in R, and B is not the same thing as C. So it's not antisymmetric. Can we remove something? We can remove either one of those. We can either remove BC or CB, and then we would make it antisymmetric. So is it possible for a relation, does it have to be either symmetric or antisymmetric? And the answer is no. This one we saw it was not symmetric because of this guy right here. It didn't have a pair. It's also not antisymmetric because of these ones in green, because that is a pair. So yes, it is possible. This is an example of that. Here's our next property. If R is antisymmetric, then for every two vertices, there is at most one edge connecting them. We see that in the graph. Okay, so here is a little bit of a more formal proof. A relation R on X is antisymmetric if for all x and y in X, if x is not equal to y, then xy is not in R, or yx is not in R. That's what it means to be antisymmetric. X and y aren't the same, then one of these two can't be in R, because they both can't be in R. So our original definition is this one, for all x and y in R. If xy is in R and yx is in R, then X is equal to y. And so I want to look at the contrapositive, because that's what I'm going to use when I prove this relationship that we're seeing. A relation R on X is not antisymmetric. Written symbolically is this one. So here's the not for all x and y. If xy is in R and yx is in R, that implies that X is equal to y. That's our original definition. I can write that by distributing my little not symbol. So when I distribute that, these for all change to there exists an x and a y, such that not this whole thing. And this whole thing is kind of going to be a little bit difficult to deal with. So what we're going to do to go from this step to this step is we're going to revisit an idea from chapter 1, which you maybe have forgotten. And that is, so if I'm saying that this statement is P and this statement is Q, P implies Q, I can rewrite that. An equivalent statement to P implies Q is not P and Q. And you can revisit chapter 1 to see, we could make a truth table for both of those and see that the truth tables for these statements are equivalent, which means these two are equivalent statements. So that's how I'm going to change this statement into this statement. For all, for xy in R and yx in R, and, oops, I forgot the not out here, and x is equal to y. So as I continue on in my proof, I distribute some more knots, and I end up, there exists an x and there exists a y, such that for xy in R and yx in R, and that means that x is not equal to y. So here we're seeing a logical proof of this antisymmetric property. Okay. Here we're going to move on to our next definition. We've talked about reflexive, we talked about symmetric and antisymmetric. So here is another property that we're going to talk about, and that is transitive. A relation R on X is transitive if for all X, Y, and Z in R, if X, Y is in R and Y, Z is in R, then X, Z is in R. So maybe I'll draw a little diagram here. This is X, Y, and Z. We're saying if X, Y is in R and Y, Z is in R, then X, Z must be in R. So this is a transitive property. We're kind of making a triangle here. If we have the peak of the triangle, then we also have this base here. Let R be a relation on X, which is A, B, C, D, where R is equal to AA, BC, CB, AC, and DD. Is R transitive? Let's look at our picture. A, B, C, and D. We've got AA, we've got BC and CB. We have AC and we have DD. Is it transitive? Let's see. Well, A goes to C. A goes to C, whoops, and C goes to B, but we do not have A going to B. This is kind of my shorthand of as I'm processing through what this transitive means. So I'm thinking it's not transitive. So here I'm going to say something a little bit more formal. AC and CB are in R, but AB is not in R. So here I'm saying this part is true. AC and CB, those are both in R, but AB is not in R. So therefore, this is not transitive. There are other reasons it's not transitive. One of them is, let's see, I've got BC is in R and CB is in R. So here's BC and CB are in R. And what you do is when you make this statement, these middle two are the same. So these outside two, that pair must be in R. So this BB must be in R, but BB is not in R. So this works with loops as well. If I have this symmetric relationship between B and C, then I'd need the loop. I actually need the other loop as well. I could write these the other way. CB and BC are in R, but CC is not in R. So I would need this one and also this one and also this one. Okay, so we've talked about a lot of properties so far. Now we're going to package some of them together in a neat way, and that's called a partial order. A relation on X is a partial order if it is reflexive, antisymmetric, and transitive. So if it has those three properties, it is a partial order. Here in example 8, let X be all real numbers if X and Y is in R if X is less than or equal to Y. and I want to show that R is a partial order. So I want to show that it meets these three properties: reflexive, antisymmetric, and transitive. So first up, reflexive. So reflexive is what I want to show is that X are X. So I want to show that X is a relation with X. So here that would be looking at this guy. X is less than or equal to X. Is that true for all X in real numbers? And yes, it is. So our relation is reflexive. Next up, is it antisymmetric? So what I want to show for this one, turn my page here, is I want to look at, okay, let's see. If X is less than or equal to Y and Y is less than or equal to X, does that mean that X is equal to Y? And I think it does. If X is less than or equal to Y and Y is less than or equal to X, the only way that that works is if X and Y are the same for all X in the real numbers. So it is also antisymmetric. And let's do the last one, transitive. If X is less than or equal to Y and Y is less than or equal to Z, then X is less than or equal to Y is less than or equal to Z, which means that X is less than or equal to Z. So it is also transitive. Since it's all three of those, R is a partial order. Here's a notation. If R is a partial order and if XY is in R, we denote that X is a partial order of Y. It's like an extra curly, like less than or equal to sign, kind of, is how we denote that. So that is not like a misprint. That is a special symbol that we use to denote a partial order. Okay. Definition. Let R be a partial order on set X if X, Y is in X and X, and that's our new special symbol, is a partial order of Y, or Y is a partial order of X. We say X and Y are comparable. Comparable means they can be put in an order. We can put them in order. But if either one of those is not true, then X and Y are incomparable. If every pair of elements is comparable, then R is a total order. In our previous example, where X was all real numbers, X and Y are in R if X is less than or equal to Y. That is a total order because you can pick any two numbers and compare them. You can put one in front of the other. So R is a total order. Let's take a look at example 9. Let X be 2, 3, 4, 5, 6, 7. X R Y if X divides Y. Is R a partial order and is R a total order? All right, let's look at what R is, first of all. R is the set that contains if X divides Y. So let's see. We are looking at 2 divides 2, 2 divides 4, and 2 divides 6. 3 divides 3, and 3 divides 6. 4 divides itself, and 5 divides itself, and 6 divides itself, and 7 divides itself. So there is all the elements that are in R. So let's see. I want to know, is R reflexive? That means it has to contain every loop. And I see 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7. So it is reflexive. It contains every loop, or every XX combination. It contains all of those. Is it antisymmetric? So let's see. Are there any pairs where we switch X and Y that are not already loops, that are not already the same? So 2, 2 is a switch with 2, 2, but we're allowed to have that with antisymmetric. I'm not seeing 4, 2 anywhere. I'm not seeing 6, 2. I'm not seeing 6, 3. So yes, it is antisymmetric. There are no switching X and Y. Is it transitive? Let's see. I go from 2, 2 to 2, 4. And then I go from 2, 4. Let's see. I go, 2, 2 to 2. So it is transitive. It's mostly transitive because I'm not really seeing this triangle structure anywhere to have this third one. So it is transitive. Since I have all three of those, R is a partial order. Is it a total order? Let's see. Let's look at some of the comparable elements. So elements 2 and 4 are comparable because 2, 4 is an element of R. But what about elements 2 and 3? Are they comparable? They are not. They are incomparable. Incomparable. And that's because 2, 3, and also 3, 2, neither of those are in R. So R is not a total order. There are pairs of elements that are not included in my relation in any direction. So this isn't the only example. 2 is also not comparable with 5 or 7. 3 is not comparable with 4 or 5 or 7. let's see, 5 and 7 are not comparable with anything else. So there are a lot of things that are not comparable in this example. Okay, another definition. Let R be a relation from X to Y. The inverse of R, denoted R with the little -1 in the exponent, that's R inverse, is defined as the switching. It's Yx such that Xy is in R. This is the same idea for inverses that we had with functions. Along with that, we're going to talk about composition. Composition of relations. If R1 is a relation from X to Y, R2 is a relation from Y to Z. The relation R2 composed with R1 is a relation from X to Z, and it's defined by all of the XZ pairs such that XY is in R1 and YZ is in R2 for some Y and Y. Let's take a look at an inverse example first. Example 10 is an inverse, and example 11 is a composition. So first up, example 10. Let X be 2, 3, 4, and Y be 3, 4, 5, 6, 7. X R Y if X divides Y. Find R and R inverse. R is going to be, let's see, so 2 divides 2, but 2 is not in the set Y, so I can't do that one. But 2 does divide 4, and 2 divides 6. All right, 3 divides itself, which is a member of Y, and 3 divides 6. 4 divides 4, and that's all of my elements of X. So that's my relation, those 5 pairs. So my inverse is going to be the set that contains the reverse of all of these. So it contains 4, 2, 6, 2, 3, 3, 6, 3, and 4, 4. Like I said, colors gotta match. There we go. That is the inverse. All right, last one, example 11. R1 is 1, 2, 1, 6, 2, 4, 3, 4, 3, 6, and 3, 8. And R2 is 2U, 4S, 4T, 6T, and 8U. So here we're seeing, let's see, X is 1, X is 1, 2, 3, and 4. And, oh wait, no, sorry. It's 1, 2, and 3. 2 and 3. And Y is these ones. 2, 6, 4, 8. Yeah, 2, 6, 4, 8. And those are also these ones, 2, 4, 6, and 8. And then Z is these ones, U, S, and T. So I want to find R2 composed with R1. So I think the easiest way to do this is to make a table with all of our X, Y, and Z values, and we'll see what comes out. X, Y, and Z. So my X's were 1, 2, and 3. The Y's were 2, 4, 6, and 8. And the Z's were U, S, and T. So we're going to look at all of our pairs and see what's happening. So let's see. This is R1 and this is R2. 1 to 2, and then 1 to 6, 2 to 4, 3 to 4, 3 to 6, and 3 to 8. Okay, so now for R2, we go from 2 to U, 4 to S, 4 to T, 6 to T, and 8 to U. So now R2 composed with R1. What color haven't I used yet? We'll do orange. R2 composed with R1 is going to be a set, and it contains the points. All right, so I'm following 1 goes to 2, and then goes to U. So I'm going to skip this whole middle row when I write these. I'm going to do 1 U. And that's that first one. 1 also goes to 6, which goes to T. So I'm going to skip the 6 and do 1T. Now we'll go 2 goes to 4, which goes to S and T. So that'll be 2 elements with a 2. So 2S and 2T. And then lastly, 3 goes to 4, which goes to S. And 3 goes to 4, which goes to T. And 3 goes to 6, which goes to T. I already have that one. And then 3 goes to 8, which goes to U. So that's a 3U. And that is all of the elements of my composition. And that was the last one for this video. I will see you next time.